All right, today we're going on a pretty wild journey, way, way back in time. We're talking about the very first chapter of our universe, right after the Big Bang. This is the story of the radiation era. So, have you ever wondered what the universe was actually like? Just moments after it all began. Forget stars, forget galaxies. This was something totally different. A universe so extreme it's almost hard to imagine, governed by a completely different set of rules. Let's dive in.
Okay, first up, the universe's first moments. We're going to set the stage here for a cosmos that was basically forged in pure light.
So to get our bearings, let's just take a quick look at a cosmic timeline. Right at the beginning, this unbelievable, super fast expansion called cosmic inflation finally comes to an end. This process, it kind of reheats the whole universe, and that's what kicks off the radiation-dominated era. That's our focus today. And you can see it slots in right before the matter-dominated era, which, by the way, is the one we're living in right now. So what exactly made this first era so special?
Well, it really all boiled down to one thing. This was a cosmos of pure energy. Let's get into what that actually means. Okay, so here's the core idea. Back then, the universe's energy density was almost completely dominated by radiation. We're talking photons, right? The particles of light. Now, matter, the stuff that makes up you, me, and all the stars, it was around, for sure, but it was just a background character. Energy in the form of light, well, light was king. And you can really see just how dominant it was. I mean, if you could go back and measure the energy density of the universe, the scales would be tipped big time. The energy from all that radiation just completely dwarfed the energy that was locked away in matter. It wasn't even a close fight. So, what was this early universe even made of? Well, picture this, incredibly hot, dense plasma, basically a primordial soup. The ingredients? You had the very first atomic nuclei, which formed in just the first few minutes. Then throw in a sea of free-floating electrons, an absolute flood of high-energy photons, and a blizzard of neutrinos. It was just this chaotic, glowing fog.
But here's the thing. This cosmic soup wasn't just sitting there. The universe was expanding, but at the same time, a super powerful force was fighting back against it, gravity. This set the stage for the ultimate cosmic tug-of-war.
Now, this might actually surprise you. See, today, we know the universe's expansion is accelerating, but back then, it was the total opposite. The expansion was actually slowing down. Yeah, it was still getting bigger, but the rate was constantly decreasing. So why?
The answer in one word is gravity. Both matter and radiation have gravity. And according to general relativity, their combined pressure acted like a giant cosmic brake on the expansion. You can basically imagine everything pulling on everything else, trying to put a stop to that relentless outward push. And this right here, this is the central conflict of the whole era. As the universe got bigger, both radiation and matter got less dense. That makes sense. But here's the catch. Radiation was losing this battle way, way faster. See, matter's energy just got diluted because its particles were spread out over more space. Simple enough. But radiation, it got hit with a double whammy. Not only was it spreading out, but the expansion of space itself was stretching its light waves. That's redshift, and that made the light intrinsically weaker. And the physics behind this is just wild. Radiation's energy density was dropping off incredibly fast. It was proportional to the size of the universe to the fourth power. That is a huge drop, way steeper than what matter was going through. And that, right there, sealed radiation's fate. It was only a matter of time before it lost its top spot. So this losing battle led directly to a massive cosmic power shift. We call it the dawn of the matter era. And believe me, this was the moment that made everything we see around us today possible. And get this. The shift happened so fast. We're talking just 47,000 years after the Big Bang. Now, that might sound like a long time to us, but on a cosmic scale, that is nothing. It's the blink of an eye. And it marks the definitive end of the universe's very first chapter. This was the tipping point, the exact moment when the energy density of matter finally caught up to and then overtook the fading energy of radiation. The radiation-dominated era was officially over. And this is so crucial, because with matter now in charge, gravity could really start to do its work, pulling matter together into clumps, planting the very first seeds for the stars and galaxies we see today. Okay, so you're probably thinking,
if this all happened billions of years ago, how on earth do we know any of this? Well, it's because we can actually see an echo from that beginning, a real legacy of light left over from that very first era.
To get it, we need to jump forward in time a little bit. The universe is now dominated by matter, but it's still this hot, opaque plasma, like a thick fog. Then, around 380,000 years after the Big Bang, something else really important happens, an event called recombination. So, what's recombination? It's basically the moment the universe finally cooled down just enough for electrons to get captured by nuclei, and they formed stable, neutral atoms for the first time. The perfect analogy is to think of that dense cosmic fog I mentioned, finally lifting.
And as soon as that fog lifted, poof, the universe became transparent. See, before this, all those photons of light were just bouncing around, constantly getting scattered by all the free electrons, basically trapped inside that plasma. But now, with the electrons all locked up inside atoms, that light was suddenly free. It could finally travel in a straight line, completely unimpeded, across the entire cosmos. And here is the absolutely incredible part. That ancient light, released all at once from everywhere, has been traveling through space ever since. And today, we can still detect it in every direction we look. It's called the cosmic microwave background, the CMB. It's a literal picture of our infant universe at the exact moment it became transparent. It's the ultimate fossil from the radiation era.
So yeah, the CMB, it's the afterglow of the universe's fiery birth. It's our direct line back to that time when light was king. And it really makes you wonder, doesn't it? What other secrets about our deepest, most fundamental origins are still hiding in plain sight, just waiting to be discovered within that faint, ancient light?